I hope you can see it. Yes, I'm a data scientist at the Sydney Informatics Hub, and this project is a collaboration with the School of Geoscience, initiated thankfully by Dietmar. The goal of this project is to develop an open source software tool to generate experimental designs. I will focus on optimizing numerical simulations for geoscience. In the next 5 minutes that I have, can give you only a very brief overview. So let's start with what is design of experiment. It's basically a statistical method to plan and conduct experiments, including analysis and interpretation of the data. And the main goal is to choose an experimental setup to maximize the information that you can retrieve from the experiment, while also minimizing the experiment cost, such as the number of experimental runs. Historically, it's been laid the foundation by optimizing in the beginning of the 20th century the agriculture yield production as well as industrial processes, but it has now a large variety of applications from variable screening, feature engineering, system optimization, and a couple of other functions. And last but not least, to optimize expensive computational simulations. The experiment stages are here. So the goal is to optimize a process with regard to multiple variable input filters or experiment settings. This can be either a real-world industrial design features such as temperature or time, let's say for a chemical process, or parameter settings for complex geophysical simulation. The experiment design is then construct an optimal test set of this parameter space for the experiment. And the experiment itself, then, which can be, for instance, a black box or complex geophysical simulation, produces then results, which are either yields or simulation predictions. And in the analysis phase, the software basically evaluates the experimental results. So two parts of the software component here. One is the actually generating the experimental designs automatically, and then the analysis part. Here we have an example of just a simple setup for a geophysical simulation. I think it was for Badlands. There are like 9 parameters, which are a mix of continuous, discrete, and can be categorical variables as well. And let's say like if you have only 3 factor or level settings per feature, you run already into a total number of almost 20,000 combinations. And the problem is in a lot of geophysical simulations, as far as I understand, is if they're very high resolution, the computation time is very time consuming and optimization is very difficult. Let's say we have traditional methods such as gradient descent or Markov chain Monte Carlo samplers. They will take thousands or 10,000s, millions of runs running this experiment, which can take days or months or even years on HPCs or computer clusters. So we have to find a solution that limits to only a fraction of the experimental designs. And that's not a very easy way to do it, since the permutations, for instance, are almost infinite. So it's there's no mathematical solution for that. And it's a big combinatorial problem in mathematics as well. To define an experiment, one has to fulfill a couple of design criteria. First, obviously, you would like to limit the experimental cost, which basically you only want to use a minimum amount of experimental runs, which is very helpful, for instance, also in pharmaceutical trials when it's humans, or for computational simulations if it's cluster computation. Then the designs should be balanced and level balanced. That means it should be evenly spaced, the settings for each factor. And another important factor is orthogonality. That means no feature should correlate with any other feature in the parameter space. And other things are high variance and minimal overlap. And there are a couple of information gain dependent efficiencies that I can't explain here in detail, like DNA efficiencies. So the software that we developed approximates in a smart way for a couple of a range of experimental runs, generates near optimal design, and we track the efficiencies that are here listed on the left as a function of number of runs, and the software then automatically suggests 3 different solutions based on the preferences of the user versus the trade-off from a minimum experimental design run to optimal and best design run. Once this experimental designs can then be used for the experiment. And once the experiment is conducted, or let's say the geophysical simulation is run, we have the results, and the software tool also allows a couple of analysis plots. Let's say you're interested in what's the best parameter space for the input parameters, or which factors are important, features importance. So you could maybe go back and select only some important features. Another plots are like feature versus response, result correlations or pairwise feature correlations, and with respect to the residual error if you have, for instance, true data for machine learning. And once you evaluate the results, it's also possible then to either select the best parameters or run more experiments where the parameters are more promising or where the uncertainty is highest. This can be done, for instance, with Bayesian optimization or other iteration methods. Here, the software package, it's called DOEGen, and it's now released, still in development, but it's available on GitHub repository. Link you can find here below. It's a Python framework, so it's easy to use. And there's a couple of functionalities that I just mentioned here. Due to limited time, I can't go through all of them, but I've mentioned most of them already. And if you haven't zoomed out yet, I'm happy to take any questions.